Okay, so I'm going to run through two examples that use real devices we might see and calculate the relative importance of the way these devices work on their efficiency using latent heat. Okay, so many of you have seen these portable air conditioners, right? So they take room air and they blow it past a cold coil on the refrigeration side and blow cool air back at the people in the room. They also take room air and blow it past the hot coil, the condenser coil that normally would be outside the building. And they take that and they blow that hot air out the window through this tube. And you can see this tube. Now, they usually only have one tube and or duct that goes to the outside. And that means that they are using the inside air and they're taking conditioned inside air and blowing it outside. And unless the house is collapsible, that means that outside air is going to get sucked into the house by that exhaust flow. And the exhaust flow is not small. So I've taken a real one that I've seen, and so the rating for this, so this is an air conditioner, the rating for it is 7,000 BTUs per hour. That means it is capable of removing 7,000 BTUs of heat from the inside. And we know that heat comes in two forms in the air: sensible heat and latent heat. We know that the fan is going to move that air past the coil and blow it outside at 180 cubic feet per minute. And that means that it's going to be drawing into the house outside air that is also flowing in at 180 cubic feet per minute. The electrical input, the energy that is put in from the plug, in from the wall, that's going to drive the motor that runs the compressors and the fans of this portable AC is 820 watts. So we're going to take our standard assumption of standard air for now. And so it's 75 degree Fahrenheit at 50% relative humidity. That's going to be we're going to use that throughout. And we're going to say that this thing is in Springfield. And I looked up the Springfield design conditions, and that is 90 degrees Fahrenheit dry bulb temperature and 73 degrees Fahrenheit wet bulb temperature. And that gives us the information we need to find that state point on the psychometric chart. So here's what our plan is. So before we go find it, we know that we need to find the latent heat. So this is the power that's going to be needing to remove the heat, that's going to be equal to the difference in absolute humidity times the flow, in this case the fan flow of 180 CFM, that's pulling air in. And then we have our consolidated constants that we talked about in the lecture. We also have the sensible heat. So that's the energy that we can sense with a thermometer. And that's, again, we've consolidated constants from the volumetric heat capacity of the air and 60 minutes per hour to 1.08 times the CFM of the airflow times the difference in temperature. So now we're accounting for the difference in humidity and the difference in temperature. And so the total energy on the air that's being introduced by the portable AC is going to be the combination of the latent heat and the sensible heat. But we're also using inside the building the electricity to run the compressor and the fans. So that's going to be whatever amount of watts it is times 3.412 BTUs per hour for every watt, right? Because those are equivalent. So now we can take our total watts. In this case, our input is 820 watts. And so our total heat that we're adding that's going to be needed to be removed is the latent heat, the sensible heat, and the electrical heat. So let's find those state points on the psychometric chart. So we know that our interior state point is 50% relative humidity and 75 degrees Fahrenheit. So that's our interior state point. Let's find our outside state point. So we know that outside it's 90 degrees Fahrenheit dry bulb temperature, and we're going to be 73 degrees Fahrenheit wet bulb temperature. So these sloping lines that line up with enthalpy lines are wet bulb temperature, right? So 70, 71, 72, 73. So where those lines cross, that's going to be our state point. So that's our outside air in the design conditions. And now we can figure out what is the absolute humidity or the humidity ratio for each of those conditions by reading over here on the absolute humidity line, right? So we look at both of those, and we're looking for the difference in moisture, the difference in humidity ratio. So in this case, the humidity ratio, we have our outside conditions here with 73 degrees and wet bulb and 90 degrees dry bulb. We have about 0.0137 at this particular altitude in Springfield. And then we know that our set point for the standard air, 75 degrees Fahrenheit and 50% relative humidity, that absolute humidity is 0.0094. So the difference is going to be the outside minus the inside, so 0.044. So let's run this calculation. So we have our inside and our outside. We have delta psi, and we're going to plug that into this equation for the latent heat. So there's our difference in absolute humidity times 180 CFM times that consolidated constants that we talked about before. So we have 3,835 BTUs per hour that have to be removed by just the latent heat that we have introduced by operating the AC, not the energy that you're trying to remove from the solar gains or the people inside the room or even other air leaks. That's just the added energy that has to be removed. Now we also have the sensible heat. So we're going to plug it into this equation. So this one, we're going to be doing 1.08 times 180 CFM times the 90 degrees Fahrenheit minus the 75 degrees Fahrenheit, and that comes out to 2,916 BTUs per hour. But we also, so now we have the amount of energy that's in the air. This is energy that we introduced in order to operate the machine, right? Because we're sucking in outside air and blowing it past the heating, the condensing coil to blow the heat that it's moved out of the building. So now we have to also account for the electrical energy that's inside. So we have the watts, in this case it's 820 watts times 3,412 BTUs per hour for every watt. So that's 2,797 BTUs per hour. So now we've got them all in BTUs per hour. And so the total heat we have to remove is the latent heat, the sensible heat, and the electrical heat. So we just add all those together, and that's 9,584 BTUs per hour. Now keep in mind the rating for the equipment is that it's only capable of removing 7,000 BTUs per hour. So here's my question for you. So you can pause to think about this a moment, and maybe pause the video and come up with your answer and feel like you know how to justify it. And obviously, if we look again, we can see that the amount of heat that's needed to be removed just by operating the portable AC is greater than the amount of heat that it is capable of removing. So the answer is that that it is B. It causes greater cooling demand than the AC can satisfy. Now, many of you have experienced these devices, and you would say, but they work. I feel cooler. And the answer is they often are successful at cooling the room that they're in or blowing cold air on the person that they're blowing cold air on, but they're transferring that heating or cooling demand to other parts of the building as it sucks in air from outside. It may be sucking in cooled air from the next room that maybe has a different kind of air conditioner, but it's adding to the overall heating demand or cooling demand for the space. So let's look at another example. And here's clothes dryers, right? So clothes dryer is typically going to take wet clothes and you're going to heat them up. In this case, it's an electric clothes dryer. So you're going to heat the air inside the clothes dryer, and then you're going to take inside air, suck it through the clothes dryer, have it heated up so it can carry the humidity off the clothes, and then blow that air outside. Now, unless you have a direct connection to the outside air, what you're doing is you're sucking in air just like the portable air conditioner. You're sucking in air through all the cracks and crannies in the building, and because you're creating a negative pressure. And so this is a fairly typical clothes dryer, 2,000 watts. We're going to say it takes 1 hour to dry a load, basically to make calculations easy on us. And we're going to say that the exhaust airflow is about 2,000 CFM. That's probably about right. You can see some dryers that are much higher and some that are a little bit lower. Now, the air conditioning in this building maintains standard air, right? 75 degrees and 50% relative humidity. And the air conditioner that we're using has an energy efficiency ratio of 13. And remember that the energy efficiency ratio is BTUH, so BTUs per hour, that can be removed, so energy removed, divided by the watts that you input. And so the watts you input are going to be in watts. So it's 13 BTUH per watt. And in this location, electricity is going to cost 20 cents per kilowatt hour. And our outside air is 90 degrees Fahrenheit and 60% relative humidity. So what's the cost of drying one load of laundry? We're going to have to account for the electricity to run the dryer, the electricity to run the air conditioner, and the additional demand on the air conditioner that is required to make up for the added air, right? So we're sucking in air, and the air has a latent heat and a sensible heat. So we've got our state points again. We've got our standard air inside, and now we've got some quite hot and humid air outside. And we're going to look for the humidity ratio. And in this case, I'm just going to give it to you as we go. So the first part, right, is we need to find the difference in absolute humidities. So with standard air, we know it's 0.094 absolute humidity ratio. And outside, you can look at it yourself, but I found it. It's 0.082, which we found on the psychometric chart. And so that means the difference, the delta psi, the difference in absolute humidity is 0.088. So the latent heat load created by operating the clothes dryer is the 0.088 times the 200 CFM times our consolidated constants. And so that's 8,522 BTUs per hour of additional load. Now we need to do the sensible heat. So that's 1.08, which is our consolidated constants for the heating volumetric heat capacity of air, times 60, 200 CFM times the difference in temperature. This should look familiar, 3,240 BTUs per hour. So the total in the air, right, is the combination of those two, the latent and the sensible. And you'll notice that in this case, the latent heat is a lot bigger. So when it's really humid, the latent heat can be much, much larger than the sensible heat. So now let's figure out the electric cost. Well, we know to do this heat removal, it's going to cost us only 1 watt for every 13 BTUs per hour, right? Because of that energy efficiency ratio. So really what we're going to do is take those BTUs per hour, the 11,762 of them, and divide them by the 13 BTUs per hour, and that's going to give us our answer in watts. So that's the watt demand. Now the dryer also is 2,000 watts. So if we remember that we're running this thing for 1 hour, this is why it makes it easy on us, right? We're going to do 2,000 watt hours and 904.7 watt hours, right? Because we're running it for 1 hour. So we combine that, that's 2.9 kilowatt hours. And if that's times 20 cents per kilowatt hour, it's 58 cents per load of laundry. So take from that whatever you will. I hope this helped you understand how to use the psychometric chart to find these state points, and then also to combine the different components of air and electric costs or electric uses to see how latent heat, sensible heat, and electric heat addition all combine into a total cooling load.